Okay, welcome back. This is the first half of Chapter 4. Now, Chapter 4 is all about sorting. I mean, there's like 8 different algorithms in this chapter, and we're going to use them all. And even there's sub-variations underneath that, so there's a gazillion choices. For the most part, we're going to be using exactly those algorithms in the book. Now, there is 1 or 2 exceptions, but I give you some really cool stuff in supplemental materials. I give you this thing called the Chapter 4 pseudocode hints. So I actually replicate the pseudocode for you. So it just makes it a little easier. So here's the insertion sort, and here's the bubble sort, and here's the shell sort. So this is what I want you to use. This is the pseudocode I want you to use. I do not want you to go, oh, let me find the merge sort on the internet and I'll just copy that. No, that's going to get you 0 points. Because part of this class is being able to look at pseudocode and translate it into whatever native code you're using, like Java. Okay? So this is important. And we're also going to instrument this guy one more time, so pay attention to that as well. Okay, so introduction. So sorting clearly is a fundamental algorithm. I mean, there's lots of things where sorts take place, right? Remember the binary search will require that the thing be sorted first? Remember that? So searching algorithms, if you're going to do something really fast, like in a database. Let's say, for example, I have a Microsoft SQL Server database, and I have an index on a particular field, and I want to find, this particular number in a field. I want to be able to get there as quick as possible. So behind the scenes, that index is sorted. Now, let me explain a little bit about some of the scenarios here. So, having a list that sorts, it makes it really, really easy. Remember, because we can get to a big O notation of log n, right? If it's sorted, right? When doing a search. So, sorting is kind of important. But let's think of another scenario. Let's say you're maintaining a list of students, and so it's all in perfect sorted order. Let's say like an Excel spreadsheet or something. And so you went through and you deleted out the rows of the students who left because they graduated, and you grabbed all the new students from a list somewhere, and you just pasted it at the end. And now you need to resort it a second time. So the first 2/3 or 3/4 of the list is in perfect sorted order, and only the bottom part is out of order. Okay? That's honestly, that is a fairly normal scenario. The scenario I just described using an index in a database, that's how indexes work. When you delete things, they just come off the index. But when you insert a record, inserts always happen at the bottom. So the bottom part of the index gets dirty. And so when it comes time to resort, you need an algorithm that was specifically designed for that scenario, where the vast majority of it is already sorted, and then the bottom part is the part that needs to be resorted. Okay? Just saying. So, knowing which one works well in what scenario is a major portion of this class. So, why are they so many? Well, the first couple of them that we're going to learn are, quite frankly, kind of simple, and nobody really uses them in real life. They're good for describing things, okay? It's an easy to understand what's going on, so they make perfect for academia where you have to learn how sorts work, okay? But after that, you probably won't use those in real life. But we're going to give you scenarios where you're going to figure this out on your own. Most of them are what's called an internal sort. An internal sort basically means that the entire sort stays in memory. Now that works, right? But what if you were sorting, millions and millions and millions of rows of data? Then I probably need a different type of sort, an external sort, where I can pull up a chunk, work on it, and put up a chunk and work on it, and then, stitch the pieces together. So internal sorts are the very, very common, but if the thing you're sorting is monstrously huge, you may have no choice but to go to an external sort. Okay, on page 79, they start talking about the insertion sort. And this is one of those ones that works fairly well if the stuff is mostly sorted, okay? Now, insertion sort works just like like, you're playing a card game, and so you've got your hand full of cards, and you want to put them in order. What would you do? You pull this one out, it goes here, and this one goes here, and this one goes here. That's what an insertion sort does. It starts scanning and goes, whoops, that one's out of order. I'll put it here. Okay, this one's out of order. I'll put it here. Okay, that's how an insertion sort works. Now, there's an algorithm, of course. Let's just take a look at how this thing could work. So here's my thing. And so this assumes this is like already gone through. And so I'm comparing like 16 and 4. And I go, wait a minute, 16 don't belong there. Okay? So I need to kind of move it around. So I think it goes there. And then 11, whoops, that doesn't go there. So I think it goes there. And it keeps just going and going and going and going and going. Now, our algorithm does not actually crack the array over, insert something, and then squish it back. It doesn't actually do that. And the reason is arrays are just not well designed for deleting in the middle and inserting in the middle somewhere. They're just not designed for that. So we kind of sort of cheat. Our insertion sort really doesn't do like what I just described with a handful of cards. It actually just puts them at the end. And so that's okay. Putting them at the end is good. Now, if we had a linked list, okay, you guys remember from your data structures course, right? Okay, good. A linked list or an array list, they have lots of different names in different languages, but an array list is a typical thing used in most languages. Will allow you to insert and delete in the middle. So if you had an array list, you'd use a completely different style of insertion sort. We're not doing that, but I'm just saying, if you had an array list or a linked list, well then this technique wouldn't have to go, wait, let me put it at the end. It'd be one of those things where, hang on a second, I'll just put it exactly where I think it needs to go. Okay, so this is figure 4.1 showing how the thing works. Let's go look at the algorithm. And the algorithm is not that complicated. It says, okay, starting at 2, do you really think we're going to start at 2? Have you figured out by now how to translate the pseudocode in the book to implementing code? I guarantee you it's not going to be a 2. It's going to be some other number, right? Okay, good. And though I pull out an element, I figure out where the location is. I figure, hey, is this location, first of all, is it valid? In other words, location is greater than 1? Or maybe some other number. And then, if this element is the one we're looking at, is bigger than that one, then move them around, boop, and then move on. Okay? So this insertion sort is not complicated. You can kind of eyeball that and go, yeah, I think I got that. I kind of sort of figure out what's going on. So, if we were to implement this one, where do you think you would put your loop count? So, would it be here? Well, what you're trying to do is you're trying to figure out where the work gets done. Well, where is the actual moving of the elements in the array? Where does that occur? Well, it occurs inside this while loop. So if you were trying to find a place to put a loop counter, putting it up here at the for loop, that's probably not going to work. Putting it at the while loop where work actually takes place, that's an excellent choice for putting a loop counter, okay? So you can kind of sort of eyeball this and go, well, does the work get done at the for, or does the work get done at the while? Okay. So let's just think about the worst case scenario, okay? The worst case scenario for an awful lot of the sorts is you have something that's exactly sorted backwards. So it goes to the first one and says, hey, are you smaller? No. Are you smaller? No, 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 no. All the way through. In other words, it has to travel the entire length. It goes to the second one. Are you in the right spot? No, 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 no. So that'd be the worst case scenario, is if things were sorted completely backwards. Okay, that kind of makes sense? So, What about the best case scenario? Well, the best case scenario would be that it's already sorted. It's already perfectly sorted. So it goes through, and this while loop never happens at all. It just goes through and says, nope, 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 done. And so, one more time. If you put your loop counter inside the while loop, and this thing was already sorted, then you would get a loop count of 0. Now, is that good? Yeah, that's okay. Yeah. It's okay to say no work took place. Okay? That is perfectly okay for a loop counter to say, man, no work took place at all because it was already sorted. Now, average case. Now, here's a little confusing because lists that are being sorted could be like the one I described where it's perfectly sorted and dirty at the end. Or it could have one where it's mostly sorted but it has some random numbers thrown in. Or it could be kind of sort of sorted but with lots of duplicates. Or it could be completely random. Now, I am not going to go through and do the math like, okay, 10% chance it's going to be this and 20% chance it's going to be that. I'm going to ignore all that. And I'm just going to assume for the sake of convenience and ease that the average case is going to be random. Now, that is not technically correct because, as I described before, the only way you would come up with average is if someone told you what is the likelihood of occurrence for it being random. Okay, but we're going to just ignore that and say, great. So, random. There's an awful lot of math associated with this. The worst case scenario goes through and comes up with n squared. Okay, I'm not going to go through all of the math. But the average case scenario, so the average case scenario starts off with this, and this is just, I'm not going to go through how they come up with all the solution. But basically it ends up with n squared. What? You mean the average case and the worst case are essentially the same? Really? Wow. That's a little weird, don't you think? So you can kind of sort of see why perhaps this sorting algorithm, before we even start evaluating the sort, can you just look at worst case and average and tell me that perhaps this is not the best sort for doing things? In a random kind of a scenario? Okay, just saying. Okay, so that's enough about that one. And so let's move on to the bubble sort on page 84. So the bubble sort is kind of sort of similar, except the way it works is I just compare the guy next to me. I say, hey, 1 and 3. And then, well, this is kind of a weird one. Again, we're halfway through the sort when they show this, so it's kind of a little difficult. What I basically do is I compare 6 and 7 and say, those need to be swapped. Boink. And then I go 16 and 10. Whoop, that one needs to be swapped. And then 16 and 1, they need to be swapped. And then 16 and 5, that needs to be swapped. See how it just goes through and swap, 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 swap. Okay, that's what a bubble sort would do. Okay. And then eventually you get to the point where, like this one, he's already filled in, 16, 15, 14, 13, 12. And so now we're doing 1 to 3, that's okay. 3 to 5, that's okay. 5 to 7, that's okay. 4 to 7, that is not okay. So we boop, boop, swap those guys around. 7 and 2, no, that's not okay. And so you just got to go through and all the way through. And then you start over again because we still have some that are out of whack. This 2 needs to be weighted over here. So it's going to go through it over and over and over. Got it? Good. Now, this is probably one of the least efficient sorts there are. But because it's so simple to do, it's just easy to implement, easy to instrument. So that's what we're going to do. All right, so we're coming up on the 15-minute mark. You guys know how this works.